Thanks. Audio working? Yeah. Dear Father, we thank you for this morning. I thank you for these students. Just pray to be with us today. Help us to, again, Lord, glorify you. What we do, pray for the CFOs today, that they would learn what they need to learn about this place so that they can make the right decision. In the name of prayer, Lord Jesus. Amen. Okay, so I guess, my temptation is to actually prove the interval of convergence theorem for you guys, but you've suffered enough. I'm not going to test on it directly. The proof is very easy to follow in the book. If you want to see me talk about it, if you watch yesterday's lecture from the other section, it's right in there. It's like right at the start. Basically, what we learn is that if you have a power series, right, and the theorem is this. I should at least state the theorem. The theorem says if you have the sum of a sub k times x minus x naught to the k power, if that converges, let me give this a name. Say s of x. If this converges at, let's say, some point, I need some point like c, then, and then I need some kind of, goodness, I need a number line to think about this here. Let's draw a picture. So like here's a number line. The center of the series is x naught in my current lingo, right? And then so c is some other point, right? Let's say it's here. All right. Then you could define the distance from x naught to c. Let's call that thing, I called it delta yesterday. I found that to be useful. So let delta equal to the absolute value of c minus x naught, all right? The distance, basically, from c to x naught. So if you do that, then the theorem that I'm trying to describe at the moment, but I promise you I won't prove, states that this power series is absolutely convergent everywhere that's at least as close as c. Not well, almost, basically on an open interval to plus or minus delta. Well, like this, let's say. So over here is, this point would be what? This would be like x naught minus delta in this situation. And if you look at this whole interval here, all up in here, s of x converges absolutely. What's that mean? That means that if you take the absolute value of this series, right, and you look at that series, it converges. So it's absolutely convergent. It's even stronger than regular convergence. So in other words, then just put it in words here. Let's say the interval x naught minus delta to x naught plus delta. Well, I'm still words. Then s of x converges absolutely on this interval, x naught minus delta to x naught plus delta. All right? So that's part one of the theorem. And the proof is really not that hard. You compare the power series to a geometric series, and by direct comparison, this result follows. I proved it with x naught equal to 0 yesterday, so you can watch that if you want. But again, the reason this is true actually is it's basically a comparison test in geometric series. That's part one of this theorem. Part two of this theorem is that if s of x diverges at, say, x equals to d, then s of x diverges at all points as far as d from x naught. That's in words. Let me draw in a picture, and then I'll give you an inequality. So like what I'm saying, imagine, no green marker, what? Come on. Really? Look at that. I've got like 30 markers up here. But no green. No. Man. Sorry. Oh, yay. Oh. Nope, not a CFA. Okay, let's see here. So I like to think about D being over here, say. All right. Oh man, this marker's doesn't have long to live. All right, so if D, so I'm saying suppose that the series diverges over here, all right? Then I said S of x diverges from all points as far as from D. So basically, if you draw rays from here out to infinity, and then, okay, so if that's D, then let's see what, I mean, I guess I could come up with some name. How far, let's say that this distance, I need to fit in some other distance. I can't quite draw it. All right, let me try. Over to here, that's horrible. The distance, what do you want to call this? Let's say epsilon, I don't know. So epsilon would be what? Epsilon would be equal to D minus x naught, the absolute value of D minus x naught. The distance from the point of divergence to the center point, right? Well then, the series, it's divergent. S of x diverges out here. And where else does it diverge? It diverges if you're that far away from the center point on the other side too. So like over here in my current picture, at minus D. Well, not minus D, but let's see here, D. How is that related to, you guys tell me, the series diverges over here. So like, how would you get this point from that point? If this distance is epsilon, you go another epsilon over here, right? So this point would be what? What's that? X naught minus epsilon, yep. So it would be D minus 2 epsilon, which would also be x naught is equal to x naught minus epsilon. Of course, this point over D, I can also write D is equal to x naught plus epsilon, right? So just to write it in an inequality, in other words, at all points as far as x naught from D, so this I can characterize more succinctly as x minus x naught greater than epsilon, where, well, to be more specific, epsilon is equal to what? D minus x naught. I don't know, the inequality, the precise statement of it, I think the number line is better. Basically, I'm just saying that, if you have a point of divergence, say 3 away from your center, then any point which is more than 3 units away from the center of the series is also divergent. Right. I think this idea is important enough that I'm going to spend another minute or two on it. I'm going to try then to transition back to more interesting things, but it's helpful to look at an example. Let's say I'll mix it up a little bit. Suppose you know that the sum of, let's say, a sub k times x minus 3 to the k converges at x equals to 4, and it diverges at x equals to 5. All right, find the maximal and minimal intervals of convergence which are possible given this data. Let me give this a name. Let's call it f of x, just for the sake of discussion. Right. So I organize my thinking with a number line. Basically, here's the point. The center's at 3, right? And I have that I'm given that it converges at x equals to 4, all right? And I'm given it diverges at x equals to 5 over here. Yeah. So my question then is, what are the biggest and smallest possible IOCs for the given series, all right? No, still just 2 CFAs, just checking. We should have another student come. It's usually like 9. When he comes, it's about 9 o'clock. Just about 9. He usually shows up for the last 10 minutes. He knows those are my best minutes. And I like this student. But he does crack me up. So you guys tell me, what's the... Now, I usually would say, call this more mathematically, this is called the maximal. And this is called the minimal. IOCs, intervals of convergence. So you guys tell me, what's the minimal IOC? What's the smallest it could be? Let me, first of all, add some like counterpoints over here. So like juxtaposed to 4, where you have what over here, like -4, right? And you also have the other side. Oh, I'm sorry, not -4. This is how much? This is how far? 1. So what should I put here? Yeah, 1, just 2, right? And then on the other side of 3, relative to 5, we've got this point over here, which is 1. Now, these actually, I actually don't know. This theorem doesn't tell me whether or not those are convergent or divergent points. It's actually an open question. They could converge, they could diverge, right? It could go either way. In principle, because I've been somewhat vague about the formula for the series, right? Yeah.
Why are they open for both of those?
I'm saying open because I don't know if it's. I don't know if I should fill it in or not.
Okay.
You guys tell me what's the smallest interval of convergence that's possible? Somebody help me out. So the theorem tells me that it's absolutely convergent from here all the way to here, right? Could you make it smaller? I already know that much is absolutely convergent. Absolute convergence implies convergence, right? So the interval of convergence has to at least include that dotted line. Do you guys see why that is? So like the minimal one would be 2, not included, to 4, which is included. That's part of our data, right? So that's the smallest IOC which is possible with the given data. What's the largest interval? So what else do we know? We also know that out here, right? Out here, past this point, it's divergent, right? And past this point over here, it's divergent. Now, it may or may not be divergent. It may or may not be divergent at 1. The theorem doesn't tell me one way or the other there, right? The specific details of the formula would guide us there. Whether or not, as we saw last time, sometimes the endpoints give us like an alternating series on one side, but a not alternating series on the other, so we gain the right point but lose the left point, or vice versa. We just don't know. What you guys tell me, what is this though? What's the largest it could be? What's that? Say again? Oh no, but it's divergent out here. That can't be an interval of convergence, right? 1 to 5. Is 1 included or excluded? 1 is excluded. 5 is definitely excluded because we're told 5 is a point of divergence, right? So it can't be in the interval of convergence. But 1 we could include if we want to be as greedy as possible. All right? So that's basically it. If you understand this example, that means you understand the theorem. All right? There's fun, slightly twisted versions of this you could ask, like, find the interval of convergence possible for, let's say, f of x, well, let's say g of x equals to the sum of 2 times a sub k x minus 3. Well, 2 times, that's not quite what I want. I want, like, let me fix this up here. Suppose you have a sub k times 2x minus 3 to the k power. How would the interval of convergence for that modified series be related to the original one? I'm just going to leave that as an open question. Maybe we'll come back to that next week if you want, or something. But we have visitors. I'm going to try to do something more interesting. What would you do, guys, though? Sorry, I'm like a moth to a flame. I can't stop. I guess my first move would be to try to rewrite it. I don't know. What do I do there? I mean, if we did something simpler, like maybe that doesn't make sense yet. This may be pretty hard. Let me make it slightly easier. Let's say it's, let me put some parentheses in here. That'll make it a little bit easier, right? The reason that would be slightly easier, this would be like, what would this be? This would be f of what? You say f of 2x. Oh, maybe I should go back. I'm sorry. I'll make up my mind eventually here, guys. Sorry. Now that would be f of 2x, right? So like, we'd either have 1 less than or equal to 2x less than 5 for the maximal case, right? Or 2 less than 2x less than or equal to 4 for the minimal case. And that would have given us what? Like 1/2 less than or equal to x less than or equal to 5/2, or 1 less than x less than 2 equal to 2. So the modified, so what we have is like 1/2 to 5/2, or 1 not included, 2 included. Those would be the maximal and minimal IOCs for g of x. All right, I'm sorry, I'm getting distracted by let's see here. So I'll try to come up with a better one of those to show you guys later. Let's go on. So I want to talk more about series calculation. So let's get back to that general topic. By the way, I'm sorry about the change in schedule. I hope it's clear from my announcement what the new schedule is. Basically, I wanted to push the test back a week to make sure you guys have a chance to really absorb all the ideas about series calculation. It takes some time to get up to speed on these things. I want to make sure you have enough time to study before the test, and I hope that extra week does it. Unfortunately, the side effect of this is to compress the last bit on like chapter 10, right? So we'll only have about 2.5 weeks from test 3 to test 4, unless I move test 4 back to the last day of class. But you really don't want me to do that, because that will make your exam week longer and will make you do worse in other classes, right? It's better for us to keep test 4 where it is, have a couple buffer days. If we need to push some section off test 4 to the buffer days, we'll do that. And that way test 4 will be kind of on a smaller subset of material. But on the flip side, you won't have as long to study it. So it's kind of a mixed deal. But I think it's in your best interest that we spend another week on series. It's an important, probably the most important thing to try to learn from this course, all right? So let's go back to some examples. Let's see if we can't find, I'm just going to do example after example after example until we get a hang of it. So here's one. If I have x plus x squared times e to the x. Find the Maclaurin series for this. All right, so what I have then is I have x plus x squared times e to the x. Well, e to the x is what? 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus dot dot dot. So I'm going to start out with this kind of example. And let's say find the Maclaurin series up to what order? What order do you want me guys to work out to? Up to order what? Order 5? I'll take that. Sounds good. So what that means then, guys, is it's pretty simple. You know, some people say that these are just, a power series is just a Texas-sized polynomial, right? But while I admire people's love of Texas and their belief in how huge Texas is, it doesn't really do justice because it's unending. I mean, power series, they're not like Texas. They're not even like the universe. I mean, they just go on and on and on and on. I don't know. Is the universe infinite? I don't know. I guess we don't know. But so you just start collecting terms, like go order by order. First of all, is there a constant term? No, there can't be a constant term because everything is formed from multiplying this one by that one, right? So, in fact, this is just going to give me, the first term is x. Can I have any other linear term? No, because x squared. So next I have x squared. How is it possible to obtain x squared? X times x, right? So I get 1. Let me use some color coding to try to explain to you what's going on here. So the first one is coming from x times x, all right? The other one is coming from what? X squared times 1, right? So this x squared times 1 also gives me a 1. Is there any other way to obtain a quadratic term here? No, right? That's the only possible products that can give us an x squared. How about the cube? X cubed times what? Let's see here. I have x times 1/2 x squared. That gives me 1/2 x cubed. And what else do I have? I have x squared times x, so I get plus 1. Plus x to the 4th. How's the possible way to obtain x to the 4th? How about x times 1 over 3 factorial? But I also have what? X squared times 1/2. So I also have plus 1/2, right? I guess you guys signed me up for 5th order, right? So, oh man, I didn't write enough, did I? So 1 over 4 factorial, x to the 4th. That's the next thing down the line. So x times, so I get 1 over 4 factorial plus what? 1 over 3 factorial. And of course, we could collect those fractions and find specific numbers there, but that's it, right? I think actually we've gone long enough and this is simple enough, you might be able to see the pattern for the coefficient of the kth term in the product, right? What's going on here? What's this one? Isn't this just like 1 over k minus 1 factorial plus 1 over k minus 2 factorial? This is k equals to 5. Is the same pattern getting me k equals to 3 here? I mean 4? Does that work for k equals to 3? Does that work for k equals to 2? Does this work for k equals to 1? Is that the pattern? Am I right on all accounts? Does it stop making sense? Oh, I don't know what 1 minus 2 factorial is, right? When I get to, I think it makes sense. I think I have to throw out this case. Nah, that wouldn't, I don't know what minus 1 factorial means, okay? But I think this formula starts making sense at 2, right? So we could say this, x squared, x plus x squared times e to the x, in fact, is equal to x plus the sum, k equals 2 to infinity of what? 1 over k minus 1 factorial plus 1 over k minus 2 factorial, right? X to the k. And there you go. 0 factorial is 1, though. That's fine, yeah. So 0 factorial is equal to 1, 1 factorial is equal to 1, 2 factorial is equal to 2, 3 factorial is equal to 6, 4 factorial is equal to 24, 5 factorial is 120. Well, you get the idea. So forth. Yeah, I think you could even simplify that expression, right? Now, when I multiply series, this is kind of a stupid example of multiplying series, right? Because, I mean, the first series is kind of a very, this is definitely not even Texas-sized. I mean, this is like Rhode Island or something. I don't know. It's very small. It's just a quadratic polynomial, right? It's technically a series, but it's kind of a series of a stupid type, right? Let's look at a multiplication of series problem which has a little bit more bite. All right, so here we go. Another example. What if we have, let's say, 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus dot, 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 and multiply that by 1 minus 2x plus 1 over 2 times, times 2x quantity squared. Oh man, I can't let you see that. It's hideous. Let's see here. I guess it's 2x squared minus 8 over 6 x cubed plus 16 over 24 x to the 4th, and so forth. All right. Let's look at the multiplication of these two and see if we can understand it. So let's see, this would give us what? In terms of constants, we have what? We got 1. How about x? Let's see, linear term, x, we've got what? We got 1. We got a minus 2, right? Plus what? Ah, man, he's early today. Let's see here, minus 2. Plus 1, right? See, I've got the minus 2 from this times that, and then 1 times x gives me the 1, right? And then x squared, what do I have? One, I got a 2. Let's see here, x times 2, minus 2, right? Let's see here, did I do this right? 2 minus 2 plus 1/2, right? I'm just going to go to third order this time, if that's okay with you guys. Let's see here, third order, what do I get? Minus 8/6, which is otherwise known as what? Well, fine, I'll just leave it at minus 8/6. We could simplify that, obviously. And then what? I've got x times 2x, so that gives me plus 2. and then minus 1, right? And then finally, plus 1/6. Let me color code what I just did for you guys, okay? So what I'm saying is, to get the third order term, I do 1 times this. That gives me this term. All right? I did x times the 2x squared. That brings me to this coefficient. I did 1/2 x squared times minus 2x. That gives me the minus 1. And finally, the 1/6 is coming from, where was I? This one times that one. Those are the different ways I can obtain cubic terms from the product of these two series. Does that make sense? What's our definition for multiplying series? You take a look at the left series, you take a look at the right series, and you just, for each order, collect all possible products which obtain the given order you're interested in. I could define this more carefully if you'd like. But that, I mean, what I'm really saying is just multiply like usual, right? This is called the Cauchy product. Can you simplify this? So this is what, 1 minus x plus 1/2 x squared. Well, that's what? That's, Is that right? That's minus 2/3 plus 1 plus 1/6, which is what?
Doesn't that be 4/3? It's 8/6.
What is that again? Oh, yeah, that would make more sense. Thank you. Thank you. Yeah, I can't do arithmetic today. So that's minus 1/3 plus 1/6, which is also known as minus 1/6. Okay, which is also known as minus 1/3 factorial. All right, now we're good. So, look, this is a stupid example in some sense. What's this the power series for? What's that? Oh, you're just saying bless you. It's like, you're so good looking. Let's see here. No, this is e to the minus x in power series form. Right? If you feed minus x into the exponential series, what happens? Minus x squared, 4th power, 6th power, the minus gets eaten. But for the odd powers, you're left with a residual minus, right? So that's e to the minus x. Do you guys agree? You see that? What's this? This is e to the x, right? And this is what? This is e to the 2x, yeah. Yesterday in the other section, I did an example, which you can watch if you want. What I did was I took x minus 1/6 x cubed plus 1/5 factorial x to the 5th plus dot, 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 dot. And I multiplied it by 1 minus 1/2 x squared plus 1/4 factorial x to the 4th plus dot, 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 dot. And you know what we got? We got 1/2 of 2x minus 1/6, 1/3 factorial 2x cubed plus 1/5 factorial 2x to the 5th plus dot, dot, dot. And you know why we got that? There's a very simple reason why we got that. That's because their example that I worked out yesterday, this is sine x, right? This is cosine x. And so, of course, when you multiply them, you should get what? You should get 1/2 of sine 2x, right? Because you know trigonometry, so that's what has to happen, right? Now, you're like, but I already know that, so I don't need to use series to prove that. Well, that's true, right? There's another way you could look at this, which is that if you defined the exponential and sine and cosine in terms of series, you could derive trigonometric identities and also identities about exponentials just in terms of series calculation. For example, you could do this. You could calculate, and I probably will subject the later section to this. I won't force you guys to watch it. But if you could calculate e to the x times e to the y, you could write that as a series, 1 plus x plus dot dot dot, and a series, 1 plus y plus dot 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 dot. And you could work out that that series is in fact equal to 1 plus x plus y plus 1/2 x plus y squared plus dot 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 dot, which of course would be e to the x plus y. In other words, you could use multiplication of series as a method to derive properties of the exponential function if you were so inclined. But anyway, let me show you some more examples. Unless there's a question. Yep.
Is it supposed to be e to the negative 2x, or is it
E to the negative 2x. Thank you. Otherwise, it doesn't make sense. Thank you. Thank you. Very good question. Thank you. Thank you. Thank you. Thank you. Thank you. Let's see here. So how about division? Well, I guess I should do another. Let's look at f of x equals to e to the x. Find Taylor series at x naught, centered at x naught equals to, say, 3. What is it? What did it do? So here, there are two ways you could think about this. I guess we could just use Taylor's theorem directly, right? So Taylor's theorem directly would say what? F of x is equal to f of 3 plus f prime of 3 times x minus 3 plus 1/2 f prime prime of 3 times x minus 3 squared plus dot dot dot. Okay, we could write it more elegantly like this. Sum k equals 0 to infinity, the kth derivative at 3 over k factorial times x minus 3 to the k. What is the kth derivative of e to the x? Right, so this is just e to the x with x set equal to 3, right? So this example is kind of silly. This is k equals 0 to infinity of e to the 3rd power divided by k factorial times x minus 3 to the k. And there you go. That, folks, is the Taylor series for the exponential centered at 3. Simple as that. There's, of course, another way you could do this example. What's the other way? So method 1. Method 1 is just, this is direct application of Taylor's theorem, all right? What's a sneakier way we can do this? I think I showed you guys this trick before. Let me show it to you again. How about this? If I do f of x is equal to e to the x, but instead of doing e to the x, I'll do e to the what? X minus 3 plus 3. That's what? That's just e to the 3 times e to the x minus 3, right? I already know the Maclaurin series for the exponential, right? So I already know that e to the u is the sum k equals 0 to infinity of u to the k divided by k factorial. So I just set u equals to x minus 3, and I'm good. So this is e to the third power times the sum, k equals 0 to infinity of 1 over k factorial, x minus 3 to the k. And then you just bring the constant inside, right? And that's the same answer. So which method is better? Direct application of Taylor's series or the substitution idea I just showed you guys? Same answer. I tend to think for this example, direct application of the Taylor polynomial is probably faster and easier, right? This substitution of adding 0 is a little bit sneaky in this case and maybe not altogether productive. However, my feelings about the red solution versus the green solution are quickly, the tables turn when I think about a different example, like, I don't know, let's see here. What if I do something a little bit more complicated, though, right? Like f of x equals to x e to the x center, the series for f of x at x not equals to 3. Well, then differentiation, I guess differentiation still will work, right? But I think it's more fun, personally, to use this recentering idea. So that's x minus 3 plus 3, right? And then e to the x minus 3 plus 3. So I get like x minus 3 times e to the 3 times e to the x minus 3 plus 3 e to the 3 times e to the x minus 3. So these that I'm circling, we can expand because those are just known Maclaurin series, right? And so what you get is like, I'll bring the e to the 3 out front. E to the 3 times x minus 3 times the sum, k equals 0 to infinity, 1 over k factorial, x minus 3 to the k, and then plus, 3e to the 3, sum k equals 0 to infinity, x minus 3 to the k over k factorial. Then what do? Bring stuff inside. There's an e to the 3 everywhere. I guess I could factor it all the way out, I'll leave it in. It says e to the 3 divided by k factorial, x minus 3 to the what power? K times that gives me what? K plus 1? Yeah. And then on the other sum, I have plus the sum, 3 e to the third power divided by k factorial, x minus 3 to the k power, I'd like to write these as one sum. I mean, I want my answer to be one sum. It's not quite done yet, right? I need to simplify my answer. So how do I do that? How about this? This starts from like linear, quadratic, cubic. This one starts with a constant term, right? But I kind of like this one. So what I'm going to say is I'm going to let j equal to k plus 1, right? And that makes k equal to what? J minus 1, right? And so with that substitution, I get the sum j equals to 1 to infinity of e to the third power divided by j minus 1 factorial x minus 3 to the j power, right? And over here, I'll just let k equals to j. So I have plus the sum j equals to 0 to infinity, 3 e to the 3 divided by j factorial, x minus 3 to the j. When we're adding series, what do we need? We need to have them, you need to be able to like add apples to apples, right? You can't add apples to oranges, so that's why I had to adjust the power here. I couldn't add these before because they had mismatching exponents, right? They have to like match up in order to add them, but also they have to have the same range. They're both going to infinity, so we're good on that. But you see the one starts at 1 and the other one starts at 0. So what do? I just throw out the 0th term on the right one and make it go from 1 to infinity. So I just write the 0th one separately. So to my final answer here is, what happens when you put j equal to 0 here? You get 3 e to the 3, all right? And then plus the sum, j equals 1 to infinity. And then we can just add these coefficients. We get, well, there's an e cubed on everything. I'll just factor that out. I e cubed times 1 over j minus 1 factorial plus a 1 over, okay. I'll get her on the next test. Let's see here. Oh man, I guess I won't. Let's see here, 1 over j factorial, x minus 3 to the j. Yeah. Oh. Thank you. All right. So, here's a weird application of this. What's the 25th derivative of f of x evaluated at 3? How would you calculate that? Well, we know Taylor's series. We know Taylor's formula. So we know that if we pick off the 25th coefficient here, that will tell me the 25th derivative, right? So all I have to do is say, well, the 25th derivative at 3 divided by 25 factorial, that has to be equal to, let's see, how do I get the 25th coefficient? Well, in this case, I just put j equal to 25, right? Well, it will be equal to e cubed times 1 over, 24 factorial plus 3 over 25 factorial by Taylor's theorem. Just comparing the coefficient from Taylor's theorem, right? And so you can calculate it. Just multiply by 25 factorial, what do you got? Let's see, remember 25 factorial is equal to what? It's equal to 25 times 24 factorial, right? So the 24 factorials cancel, and you're just left with a 25 here plus 3. So it's equal to 28 times e to the third power. If I give you a question on the next test where I ask you to calculate the 70th derivative of a function or something, you should understand I'm not actually asking you to differentiate the function 70 times. It's a standard trig problem. But it's one of the weird applications of series. You can actually use multiplication series and other series manipulation to calculate derivatives in the same way that you can use derivatives to set up a series. There's a give and a take here, yeah? I have so many more tricks to show you about geometric series. We'll do those next week, but have a good weekend. If you have any questions about your homework, you can email me. I'll try to give you hints.